All right, didn't get any questions regarding the homework or anything with the courses. Again, these are not lessons or lectures, so you're tuning these. These are office hours, so if I don't have questions, I'll answer them. Coming up on probably exam 2 sometime, I'm guessing next week for all my courses. Keep in mind for the online 152 courses that these next exams, 2nd, 3rd, and 4th, these are all online. They're not going to be at the ELTC, so you're just going to take them. They're going to be directions. Big thing with these is that we're using the Respondus proctoring software, and you do need to upload your work within 24 hours. No work means no credit. Even if your answer is correct, you still get a 0 because you can't prove you got that answer. And submitting your work like 3 or 4 days later looks really suspicious. So when you take your exam, make sure you can take pictures of your work. I recommend loading to a Word document, submitting the Word document up into Blackboard. If you're having issues to upload, please email me pretty quickly. That's about it. So if you got questions, post them up in the chat. Otherwise, I'll be here getting work done. So I got a question about what do we mean by the spin of electrons? And actually spin is a very poorly defined concept in the sense that we don't really understand it. We have analogies for it. We know it is a fallout of quantum mechanics, but as far as what spin specifically represents, we don't know, but we do know how it behaves. So there's a lot of analogies that get used to describe spin. The worst one is actually the magnet analogy. And the magnet analogy goes that an electron has a north and a south pole, and spin describes whether you're looking at the North Pole up or the North Pole down. The reason why this is a bad analogy is that if we look at NMR, nuclear magnetic resonance, the way an NMR measurement is done is that we have a strong magnetic field, in this case represented by the letter H, and this magnetic field does have a north and a south pole. This would imply when you stick electrons or anything with spin in it, like in this case for the NMR, the nucleus has spin, this would imply all the poles point north. Well, they don't. There's a 50-50 chance of them pointing up or down. So the better analogy for spin is actually what's considered angular momentum. And the criticism, we'll start with the criticism of this analogy, is that angular momentum is if you take a wheel and you spin it, and you try to turn the wheel as it's spinning, it's going to fight you. It's not going to let you turn the wheel because as the wheel spins along, it kind of balances out all the forces. So the issue with this analogy is that if we have a spinning wheel, what's stopping it from slowing down? How do we transfer spin? These are all phenomena that are observed. So that is legitimate criticism, but it will actually explain a lot of what we see. So if we think of an electron instead of being a magnet, but instead of spinning top. So we have our electron, and it's kind of like a flywheel spinning around, and the magnetic field here is the gravity. Well, there are two ways you can spin a top and it will be stable. One is clockwise, the other is counterclockwise. And both of these will be stable if you're just thinking about a spinning top and gravity. And actually where your spin number comes from, so the spin of an electron is 1/2, is the number of stable states times the number of stable states of a, I'm sorry, kind of catching the window back there. If you take twice the spin number, oh, that didn't help either. The number of stable spin states is twice the spin plus 1. So if we have a spin of 1/2, 2 times 1/2 is 1 plus 1 is 2. It means that in a magnetic field, there are two ways we can orient the electron in this spin state, and it would be stable. So that would be spinning clockwise or counterclockwise relative to the magnetic field. So this explains why when we look at something like NMR, so for a 1H nucleus, this nucleus has a spin of 1/2, and we have a magnetic field. The nuclei can be spinning clockwise or counterclockwise, and both would be stable. This is why underneath strong magnetic fields, electrons and nuclei, there's a 50-50 chance of seeing them spinning one way or the other, because both are stable spin states. And you're probably not going to have that many that are caught perfectly between, like perpendicular to the magnetic field. Now, this spin analogy also helps us explain when we get away from non-spin 1/2 nuclei. So if we have an electron that's spin 1/2, if we have a proton that's spin 1/2, if we have a neutron that's spin 1/2. But we have something like deuterium. So H2 actually has a spin of 1. So where does this integer spin come from? Well, we have a proton with spin of 1/2 and a neutron with spin of 1/2, and if we were able to probe the spin states within a nucleus, we would see that we actually have two unpaired spins. So the analogy here is that we actually have a gyroscope within a bigger gyroscope. So this is kind of like if you ever go to like carnivals and they've got the thing where you sit inside of it and they start spinning the 3 different wheels around you. That's what you're seeing. So we have an inner gyroscope that can be spinning clockwise or counterclockwise, and then we have our outer gyroscope that can be spinning clockwise or counterclockwise. So we have all 4 spin possibilities, both clockwise, one counterclockwise, and both counterclockwise. We actually have 4 possible spin states here which are stable, and we see this with when we measure the spin of the spin 1 nuclei and 3 had nuclei and things like that, we actually end up with multiple spin states. Now I know I said 4 there. Number of spin states here is 2s plus 1. There are 3. So we have clockwise, one counterclockwise, both counterclockwise. Those are your 3 spin states. And so every time we add a spin, we just add another wheel here. And again, the mathematics start getting a little complicated. It gets a little hard to see what's going on. But that's kind of spin in a nutshell. Underneath the magnetic field, it's going to act like the magnetic field is going to act like gravity, and the spin is going to act like a magnetic is going to act like a gyroscope. It's going to act like a spinning wheel, and it's going to give us a stable spin relative to that magnetic field. Now, there are also other implications about spin. Those are going to be kind of more of a graduate level course. I took a graduate level course where we went into how spin interactions work. This is where the analogy of this angular momentum is going to start breaking down when you start discussing things like spin diffusion, spin coupling, things like that. But if you're just looking for kind of like an undergraduate level of spin, I would definitely say that this spinning wheel analogy is the best one for you. All right, so a question about optical isomerism and conformations. So we'll start with conformations because they're the easiest to explain. So all a conformation is are molecules that are related by carbon-carbon single bond rotations. So when we draw a molecule, so let me build a pretty generic one here. We tend to draw what we would consider the lowest energy conformation of the molecule, the one we would expect to see. So let me build my little molecule. I've got 2, 4, 6, 7. So let's say I've got this molecule. 2, 4, 6, 7, so 2-methylhexene. And we draw it this way because this would make most sense. It puts everything far away, and if we build the molecule, this was what it would look like. But there's nothing stopping the molecule from looking like this. Like, it can fold in on itself, and there you go, you've got the molecule. So because we don't have any restrictions on bond rotation around carbon-carbon single bonds, these molecules here are the same even though they're not drawn the same, because there's a very low barrier here to getting it to straighten back out. So we would not consider them different molecules even though they're drawn differently, because there's no barrier to taking them from this coil loop back to this loop. Now again, we typically draw it this way because this is what we expect to be the lowest energy. But the energy barrier to get it here, really, it's accessible. You can get to that at room temperature. Now, what we can't do is take a double bond and rotate it. Or triple bonds. We can't rotate it. Well, okay, triple bonds kind of misleading. We can't take double bonds, and we can't take double bonds and rotate around them. So we can't draw this, because in order to do this, we'd have to break this bond in order to make that happen. And with a lot of modeling kits, the way you see it is it'll force you to put 2 bonds between 2 atoms, and you try to rotate around those double bonds, and it just won't let you do it. What's happening here is that that pi bond isn't between the 2 atoms. It's actually above and below the sigma bond, which is between the 2. So in order to get these 2 halves to let go, they have to break the bonds, turn, and then reconnect. Breaking that bond takes energy, and that's not accessible at room temperature. Now, for optical isomerism, usually what we're talking about here is chirality. So to meet the condition of chirality, we have to have a carbon with 4 unique groups around it. And the effect of chirality comes about, okay, take a step back. Chirality in organic chemistry means that we have a single atom with 4 different groups around it, and pretty much we're going to treat carbon as the only chiral atom with an organic molecule. You can definitely find exceptions to this, especially with nitrogen. Generally speaking, though, 99% of the chiral molecules we talk about in organic chemistry, carbon is the chiral center, meaning it is the atom that contains the 4 different groups bound around it. Now, the reason why we get to this optical isomerism is that when light passes through the bonds of a given molecule, it actually bends and rotates. And for a achiral molecule, something that doesn't have any chiral centers in it, there is no net rotation because all the atoms, because they have this type of symmetry, bend the light in the same amount both clockwise and counterclockwise. This isn't true for chiral molecules. So here I have a carbon that has an ethyl group, a propyl group, a methyl group, and a hydrogen. These are 4 separate groups. They're all going to bend the light differently and not cancel each other out. And because we don't get this canceling, if we were to have polarized light, which was oriented in the z-axis, it would actually rotate off axis. And so we get these optical isomers, things that they change. You can't, okay. 1, they're optically active, meaning that they're going to bend light. 2, they can't be interchangeable with each other. So there's no way that you can rotate this molecule to get this one back. So chiral molecules have mirror images, meaning that if you, use the example of this of your hands. Your right hand is a mirror image of your left hand, but there's no way I can turn my left hand and make it look like my right hand. They'll always be mirrors of each other. Now, if we take something like this pen, if we take the mirror image of this pen, I'll just use, do I have another one? Yes. Even though this one's red, if I take the mirror image of these, they're going to look the same. If you didn't see the red and blue, you wouldn't be able to tell that these were mirror images of each other. This isn't true of left and right hands. So optical isomerism comes about from chirality. A molecule can have multiple chiral centers. We typically start you out easy with one chiral center. All you're looking for, enantiomer. Yes, the mirror image is going to be the enantiomer. Now, all single chiral molecules only have, you have the molecule and its enantiomer. If you have two or more chiral centers, the enantiomers are the ones where all the chiral centers are flipped. The diastereomers are the ones where only one chiral center is flipped. So let's say I took this molecule and I also threw a fluorine on it. These two are not enantiomers, these two are diastereomers. So these two are diastereomers. Missing one somewhere. These two are enantiomers. Oops. These two are enantiomers, and these two are diastereomers. So if you have more than one chiral center, you end up getting enantiomers only if all the chiral centers are flipped. If they're not all flipped, so at least one is flipped but not all, you have the diastereomers. But yes, these are going to give rise to optical isomers that they give different rotations. And that's typically how we diagnose them, is that we look at the optical activity and we see that they have different optical rotations for the same concentration, same solutions, for solutions of the same concentration. So meso complexes really aren't that bad. A lot of students get intimidated by them. The harder part with meso complexes is just identifying if a molecule is meso, which actually is a lot easier if you're using a Fisher projection for linear molecules, and for ring molecules it's super easy. So a meso complex is one where we have the enantiomer is the same thing as the starting molecule. So meso complexes are their own enantiomers. Now, meso does not mean achiral. It will act like an achiral molecule because it won't be optically active and it doesn't technically have an enantiomer, but they have chiral centers. That's what makes them different from typical achiral molecules. So if we look at something like cis-1,2-methyl cyclohexane, this is a meso complex. Whereas the trans version is not. So why is this one meso and this one isn't? Well, if you look at it, the big tip-off that a compound is a meso complex is if it has a mirror plane running through it. So if you look at this molecule, it has a mirror. And the thing is that there is a one-to-one correlation on opposite sides of this mirror. So these are equivalent, and this is the mirror image of this. So if we work out the symmetry 1, 2, 3, that's going to be R. Because this is mirror plane, that's going to be S. This is R and R. What happens is that with a mesocomplex, the chiral centers actually cancel each other out in terms of optical activity. So if we have R and S centers have equal and opposite rotation, so the alpha of the R complex is going to be just the negative of so the alpha here refers to the optical rotation. They have to be equal and opposite in magnitude. Well, let's say the alpha here is 6 degrees. When it hits the S, it's going to go minus 6 degrees, and they're just going to cancel each other out. This isn't true of the non-mesocomplex. So this one has an R, this will rotate at 6 degrees, and this will rotation an additional 6 degrees. So what you have with mesocomplexes are, within the molecule, there is a mirror plane. And on opposite sides of the mirror, each chiral center has the opposite symmetry for its corresponding group. So for here we have an R, on the opposite side we have an S. This isn't going to be true for the non-mesocomplex, where if we were to draw the mirror plane in the same place, the mirror of an R is not an R, the mirror of an R is an S. So for cyclic molecules, these are very easy to diagnose. If you see a mirror plane, the complex is meso. If you have a linear molecule, it gets a little bit more challenging. Now, this is going to, this is just a bad example because you can see that it's got a mirror plane. But if we look at this one, so we've got, there we go. So if we look at this one, these two are chiral centers. So this one we have highest priority is 1, 2, 3. So this is going to be R. Highest priority 1, 2, 3. It goes in opposite order. This is going to be S. If you look at it and you see that mirror plane, what makes this compound meso is that the R and the S are mirror images of each other. So you have a mirror plane running through it. Whereas if we did this molecule, we would end up getting not mirror images. It would end up flipping this S on R. So why are they their own enantiomers? Well, if I take the mirror image of this molecule and reflect it, so I reflect that one to here and this one to here. Well, actually, no. So this would be the mirror image. All I've done is really rotated 180 degrees around that plane, and I can get it right back. So I have taken a mirror image here, but the mirror image is related to rotation. And again, that's an artifact of this mirror plane running through the molecule. So what happens with this plane of symmetry is it basically gives you a special operation in point groups, which is inversion. So if you go to the inorganic definition of chirality as something that lacks an inversion plane or inversion operation, that mirror plane gives you the inversion operation, and that's what makes it achiral. Inorganic chemistry is going to cover a lot more examples of chirality that don't involve carbon. It's a lot harder to see. You have to learn point group. Point groups will tell you certain point groups are chiral, most are not. That's why most molecules are achiral. But for the organic definition, we kind of stick to the 4 different groups. Because we stick to the 4 different groups, we kind of had to add the special caveat about the mesocomplexes because we're not referring to the symmetry of the molecule. So generally speaking, nitrogen with a lone pair is not going to act as a chiral compound because we have rotation around the carbon-nitrogen bond. You can occasionally get one, but what it's doing is kind of bending the molecule. So if we have, we'll just do methyl, ethyl, isopropyl. I don't think you necessarily get chirality with those because the nitrogen, those lone pairs can actually move around, so we can start getting switching. The bigger thing you kind of see with chiral nitrogen compounds is actually when you get the ammonium complex. So you have the nitrogen with a hydrogen, ethyl propyl. That's going to start impacting the chirality because that is actually a four center. It's not carbon, but it's a four center that has four different groups in it. Again, you're kind of getting more into kind of esoteric chirality examples. Other big problem with this type of example is that because that nitrogen is labile, pops on and pop off, no matter what you make, you end up generating a racemic mixture of both the R and the S forms of the nitrogen. So again, nitrogen with a lone pair, to the best of my knowledge, that doesn't actually form a chiral center. At least if it does, the books tend to gloss over that really, really, really hard. But from what my understanding is that that lone pair can actually move around. So let's say you have your two groups and your lone pair can actually pass between the two. We get a lot of lability with that. But again, when nitrogen picks up, because that lone pair, it can pick up something on it. If it does end up picking up something on it, it ends up getting a coordination with it. That's when you start getting an atom with four different centers on it, and that begins to meet our definition of chirality. But yeah, with nitrogen, I don't think we treat the lone pair as a lone group. We just treat nitrogen as having three groups, and there's no chirality associated with that. Now, things like there is an example of nitrogen that does have chirality, and this is the phosphorus analogy. Triphenylamine. That is chiral. Again, we're kind of getting into esoteric. This is going to dance more into inorganic chemistry. The analogous compound here is triphenylphosphine. And the reason this ends up being chiral, it's not predicted by our definition of chirality in organic chemistry because each of these only have three groups. But the benzene rings are too big to lie flat next to each other. So what they'll end up doing is they'll end up tilting to accommodate each other. So it's not shown here, but you basically have the rings kind of stacking on top of each other at an angle. Well, it looks like a boat propeller at this point. So they can be tilted clockwise or counterclockwise depending on if you spin them, how they would force fluid through it. So this is an example of a chiral molecule, but it doesn't meet our chiral definition. And the reason it doesn't meet our chiral definition is it doesn't have four groups, but it is chiral by nature of the fact that when these molecules do align, those benzene rings aren't perfectly sitting out in space. They're actually having to tilt to accommodate each other, and they can tilt one way or the other. We have to account for which way it's tipping, clockwise or counterclockwise. Again, this is very heavily inorganic chemistry. They care about this with the triphenylphosphine. It is technically chiral, but from what I recall, I don't think it actually has an optical activity associated with it. But yeah, I have yet to see an organic chemistry course that really kind of delves into chirality beyond carbon. It is very much an inorganic thing. And if you look at the symmetry group of this ends up being C3. I don't even think it's C3V. That C3 symmetry, I think, is what makes it chiral. I could be wrong. It's been a long time since I've done, I never even taught an inorganic chemistry course. But yeah, nitrogen can do it because it can form the fourth bond, so it can technically meet our definition of chiral in carbon land. But again, organic chemistry is going to focus pretty much exclusively on the chirality of carbon. Torsional strain versus van der Waals strain. So torsional here is going to be turning at an angle. I'll explain this. So van der Waals strain is just steric strain. So van der Waals strain is that we might draw something like this, but the reality is that the CH3 group takes up space. And the van der Waals and steric are pretty synonymous here. Van der Waals is interaction between electron clouds. So steric strain comes about from the same thing, that these groups hanging off of it, they do take up space and they start pushing off of each other. Torsional strain can come from van der Waals strain, but there are other things that can cause torsional strain. So torsional strain is the strain along this bond. And an example of that would be van der Waals strain, where these two groups start getting close to each other. There's a resistance to making these two sit in plane with each other. But we can get it from bonding. So what keeps rings as rings is that in order to really start rotating them, we have to start stretching out bonds. And so that's not a van der Waals effect, that's a bond breaking effect. So the bonds within rings can't turn as much as they can in linear molecules. Linear molecules can turn a full 360 degrees, whereas with the rings, you're probably looking like maybe 60-degree turns before you start, before the rotation gets blocked by sheer merit of the fact that you're having to break bonds. There can be other effects that strain a bond. So if we end up getting a zwitterion, something that has both positive and negative charges, we can put strain on the bond by mirror of the fact that we have opposite charges in the molecule that are starting to bend and try to turn the single bond. So van der Waals strain will give rise to torsional strain, particularly in linear molecules, by sheer merit of the fact that these things do take up space. But not all torsional strain is due to van der Waals strain. Generally speaking, we're usually referring to van der Waals strain when we say torsional strain. But other things can give rise to torsional strain, such as having to make or break bonds in order to engage in rotation. You can have Coulombic effects. These are charge effects within the molecule that end up generating strain in the molecule. So I would say just keep in mind with torsional strain, generally speaking, we're going to refer to van der Waals, but we're not always speaking about van der Waals. It can definitely come about from other sources. All right, so that's it for office hours today. Do enjoy actually having questions to answer during these, so please feel free to come and ask questions when you want to. Next live stream, I believe, is next Monday. So I'll see y'all Monday.